Hello everybody, myself Jyoti and this is 7th lecture on Raman spectroscopy. So in the last lecture we discussed pure rotational Raman spectra of linear molecules. In this lecture we will study the pure rotational Raman spectra of symmetric top molecules. We have already studied the classification of molecules based on their rotational behavior. So we know that in case of symmetric top molecule, the principal moments of inertia along x, y and z axis, they are such that the principal moment of inertia along y axis and z axis, it is equal, and it is not equal to principal moment of inertia along x axis. And Iz is the moment of inertia about the axis of symmetry of the molecule. Now here, as we have principal moment of inertia along yz axis and x axis as well, so there are two directions of motions, or we can say there are two degrees of freedom in which the molecule can absorb or emit energy. So here, in order to explain the rotational state of the molecule, we will need two quantum numbers. Now here we will consider two quantum numbers j and k, and it should be understood that this k is different from magnetic quantum number, because here this k quantum number, it will also take 2j plus 1 values. Generally what happens, we talk about mj which can take 2j plus 1 values, but mj is different and k is different. K specifies the component of vector J about the axis of symmetry which remains in the same position relative to the molecule, whatever orientation the molecule is in. So now we will study the selection rules, and depending on that, what kind of spectra we get. Now we have already studied the quantum theory, and it shows that two quantum numbers j and k describing a rotational state of the symmetric top molecule are associated with total angular momentum vector j and projection of vector j on the axis of symmetry respectively. So j and k, we are going to need these two vectors. So we have the formula j, it is equals to under root of j into j plus 1 h cross. Now k, it can take values from minus j to plus j, total 2j plus 1 values. When we solve the Schrodinger's equation for the energy values which are allowed for the particular molecule, we are not going to solve the Schrodinger equation, we are just writing this equation directly. So EJK, energy of the molecule with quantum numbers j and k, it is given by the formula B j into j plus 1 plus a minus b into k square. Now where this b is h square upon 8 pi square iy and a is equals to h square upon 8 pi square ix, we know that b is a rotational constant. Here we are having two rotational constants, b and a, as we have used two rotational quantum numbers. And j, it can take values 0 1 2, but above equation shows that except for k equals to 0, energy levels for any k are doubly degenerate. So now here, when a radiation of frequency nu ex, suppose nu excitation, it is the radiation of incident frequency, it is made to incident on a system of symmetric top molecules, then there will be an exchange of energy which will take place between a photon, because when I'm saying radiation it consists of photons. So exchange of energy will take place between photon and molecule based on the selection rules. Now here the selection rules will be delta k. In case of linear molecules, we had two selection rules, delta j equals to 0 and delta j equals to plus minus 2. Here we have the selection rules, delta j equals to 0, plus minus 1, plus minus 2 for k not equals to 0, delta j equals to plus minus 2 for k equals to 0. Now we will see the selection rules one by one. Now selection rule delta k equals to 0. Simply, that means that change in rotational quantum number for axial rotation is 0. That means there is no exchange of energy taking place between molecule and photon. And the changes in angular momentum about the top axis will not give rise to Raman spectrum, and such transitions are called as Raman inactive transitions. Now, even if same kind of explanation we try to give classically on the basis of polarizability ellipsoid consideration, see, we can explain the Raman effect classically and quantum mechanically. When we try to describe Raman effect in terms of quantum mechanics, we consider the scattering which is taking place between photon and molecule. And when we try to explain it classically, we are trying to explain it with the help of polarizability. So even if we try to understand it from the polarizability ellipsoid consideration, polarizability ellipsoid of a symmetric top molecules has a circular cross section at right angles to its own axis of symmetry, and so a plane rotation about the top axis produces no change in the polarizability. And we know that so as to get Raman spectra, there should be change in polarizability. As here there is no change in the polarizability, there will not be any Raman spectra, and that is how we say that the Raman spectra is inactive. Now delta J equals to 0, as we have seen in the earlier case of linear molecules as well. Delta J equals to 0, it will give rise to unperturbed line or unmodified line or parent line. What is unperturbed line? When we study the Raman effect, the incident is made to fall through the sample, and the scattered radiation, it consists of three radiations, one which is having frequency same as that of the incident radiation, and other two slightly higher and slightly lesser frequency as compared to the frequency of incident radiation. Now when I say delta J equals to 0, the meaning is there is no exchange of energy between photon and molecule, and the scattered radiation will consist of a frequency which is same as that of the parent incident radiation, and that is how this delta J equals to 0. It gives the unperturbed line. Unperturbed यानी जिसका frequency same है as compared to incident frequency. Now delta J equals to plus minus 1 के corresponding जो भी lines रहेंगे उनको हम बोलते हैं R branch lines. Delta G equals to plus minus 1 यानी transition will take place between successive energy levels. That means EJ plus 1 से EJ में या फिर EJ से EJ plus में transition होगा. When we say delta G equals to plus minus 2, that means transition is not taking place between immediate energy levels but with एक level छोड़ के, like EJ से EJ plus 2 में transition हो रहा है या फिर EJ plus 2 से EJ में transition हो रहा है. That corresponds to delta G equals to plus minus 2, and these lines corresponding to delta G equals to plus minus 2 are called as S branch lines. So when we study the pure rotational Raman spectrum of symmetric top molecules, it is basically superposition of two series of lines, R branch lines and S branch lines. So if we calculate the frequencies of lines of R branch, you will get nu r is equals to nu excitation plus minus b dash 2j plus 2. ये ऑलरेडी हम लोगों ने पहले किसी एक्सप्रेशन में फाइंड आउट किया था. एंड इन केस ऑफ लीनियर मॉलिक्यूल्स वी हैव ऑलरेडी कैलकुलेटेड दिस nu s equals to nu excitation plus minus b dash 4j plus 6. This equation corresponds to transition taking place from EJ to EJ plus 1 or EJ plus 1 to EJ, and this transition corresponds to transition from EJ to EJ plus 2 or EJ plus 2 to EJ. We have already solved this kind of equations earlier. That is how I haven't given the derivation again. Here the value of J, it is 1, 2 and so on. And for S branch lines, you will get nu S is equals to nu excitation plus minus B dash 4J plus 6. So इस expression के लिए for nu S equals to nu R branch lines, J varies from 1, 2 and so on. And for S branch lines, the J varies from 0, 1, 2 and so on. Now in both the equations we have here plus minus. This plus minus represents Stokes line and anti-Stokes line. So let us see. So if you will calculate Raman shift, what is Raman shift? Raman shift is given by incident frequency of incident radiation minus frequency of scattered radiation. So यहाँ पे what we will do, this is new incident frequency now. So nu excitation minus nu r. If I take this difference, I will get plus minus b dash 2j plus 2. Here also nu excitation minus nu s. If I do that, I will get plus minus b dash 4j plus 6. So that is how I can calculate Raman shift. So delta nu r, Raman shift corresponding to R branch line, it is given by plus minus b dash 2j plus 2, where j varies from 1 to and so on, and delta nu s, Raman shift corresponding to S branch lines, it is given by plus minus b dash 4j plus 6, where j varies from 0, 1, 2, 3 and so on. So in first equation, j cannot be equals to 0, because if j is 0, k is 0, and if k is 0, delta j cannot be plus minus 1. So that is how here we have j starting from 1. So if you will check the Raman spectra, or here what you can do, substitute j equals to 0. If I substitute j equals to 0, I will get 2b dash plus minus 2b dash. If I substitute j equals to 1 here, I will get 1 into 2 plus 2 means 4b dash. Similarly, 6b dash, 8b dash, 10b dash, and so on. So for I get R branch lines at a distance of 2b dash, 4b dash, 6b dash, 8b dash, and so on. And if I calculate this, if I substitute j equals to 0, I get first line at 6b dash. Um, then j equals to 1, so I will get 10b dash, so 6b dash, 10b dash, 14b dash, like that. So here you can see for R branch lines I am getting first line at 4b dash and later on at a distance of 2b dash. First line 4b dash में मिलता है and बाकी सारे lines जो है वो 2b dash distance पे है. एक second. So here you can see 2b dash, 4b dash, 6b dash, 8b dash, these are the R branch lines. So lines which are towards the left side of the new excitation, they are S branch lines or Stokes lines, and here the lines which are there, they are anti-Stokes lines. Now for S branch, we know that the first line, it is at a distance of 6b dash, and later on the difference between any two successive lines of S branch, it is 4b dash. So 6b dash, then 10b dash, 14b dash, 18b dash, and so on. And if, as we have R branch lines and S branch lines both, if you check the complete spectrum, so I will get 4b dash line of this R branch here. Then 6b dash may is this line is also there, R branch line is also there, and S branch line is also there. So naturally in the complete spectrum I will get more intensity corresponding to 6b dash because I have R branch and S branch which are superimposing on each other. Next line will be 8b dash, which will be from R branch. Next line is 10b dash, which is because of the superposition of these two, and that is how it will be intense. So in R branch lines appear at 4b dash, 6b dash, 8b dash, 10b dash with respect to excitation frequency. In S branch lines appear at 6b dash, 10b dash, 14b dash with respect to excitation frequency. It shows that every alternate R line overlaps on S line, and the overlapped lines are obviously more intense because यहाँ पे देखो 4b dash 6b dash नहीं match हो रहा है, but 6b dash these two lines are overlapping. Then just a second, then 10b dash 10b dash lines are overlapping. Like next one is 14b dash, 14b dash will be overlapping. So for those particular lines the lines will be more intense. So the complete spectrum shows that line spacing in the rotational Raman spectrum of symmetric top molecules, it is 2b dash, whereas for linear molecules it was 4b dash. We have seen that in the earlier lecture. And it further shows that there is a marked intensity aberration due to overlapping of R branch line and S branch lines at 6b dash, 10b dash, and 14b dash. And this alteration of frequency of spectral lines in this case, it has nothing to do with nuclear spin. So this is all about the pure rotational Raman spectra of symmetric molecules. Thank you.